Welcome to revision for 2019 exams in January. This is the first in the series, and this will be dealing with R101, which should be, in the majority, the Year 11 students. And we're looking at R101 Engineering Principles for the Cambridge National Award, a certificate in Principles in Engineering and Engineering Business, which you're studying in Year 11 at the moment. Okay, we're going to go through it and try and work reasonably quickly and just deal with the main sort of fundamentals or principles that you might need to be able to answer this paper. Now the papers are usually divided up into 6 questions of 10 marks apiece, and each question tends to deal with one sort of topic area. So this is dealing with mechanical engineering, and it's dealing with sort of some basics of gears, levers and pulleys. And here we have a lever setup. It says here to show the position of the fulcrum. So levers always have an effort, a fulcrum and a load. So the fulcrum they're looking for you to label is here. So for 1 mark, all you need to do is label the fulcrum, like so. Now in addition to that, from a sort of revision point of view, you should be aware that there are 3 classes of lever. So this is a class 1 that you need to be aware of, and a class 2 has some sort of pivot or fulcrum at the end, with the effort being at the other end, put E for effort, and the load being in the middle, like so, put L for load. Now I've drawn it a little bit like this because this is a classic example of, or a classic example of a class 2 would be a wheelbarrow. So if asked to give an example, a class 2 would be a wheelbarrow. Now a class 3 has, again, a fulcrum at the end. It has a load at the opposite end, and it has the effort acting in the middle. An example of this might be your arm. So for example, there's your elbow, there's the effort from your muscle, and there's the load being carried in your hand. So that's a class 3 lever, and you will need to know class 1, class 2 and class 3. In addition to that then, it says calculate the right hand, I'm going to just underline that, the right hand moment of the lever mechanism. The right hand is this side. So it's asking to calculate a moment. A moment is force times distance. So the force is 150 newtons. Always include your units. And it's times the distance of 2 meters. So the moment of force is 300 Newton meters. Okay, now really important that you read questions very carefully. So let's just go through this one. It says state the effect on the effort, so we're here, required to move the load's there, if the distance between the fulcrum and the load, the distance between the fulcrum and the load is increased, that's this distance. If that gets bigger, what happens here? Okay, we know with a lever, if you've got a moment of force on this side, it has to be equal on that side. So right now we've got 300 newtons meters because it's 150 load times 2 meters. So if we make that bigger, and what I would do is I'd do a little, let's make it 1 meter bigger and see what happens. So 150 newtons and make that 3 meters. Well, what would that equal? Well, 3 15s, so that's going to be 450 Newton meters. So what's happened? It's the effect on the effort required to move the load, well, the effect is that it needs to be bigger. And I'd be happy with more or increased, but this is the clue. This really helps me as an examiner see that, you know, you understand what the moment of force is. You've worked out what happens if the load's increased. So that's a good way of responding to that. Read the question. Read the question. Okay. Now we've gone question 1A, and these are all related to this image. Now we've got B, and this is something new now. Give one other method of moving a load that would give a mechanical advantage. Well, another method. Levers one. What other methods have we got? Well, these are gears, pulleys, like so. Yeah, gears and pulleys. That would give you, one of those would give you a mark. So just moving on to this next question, because this question, the answer spaces go over the page. Don't be surprised that a question goes across a number of pages or over a page. Students sometimes don't miss a question simply because it's on the next page over. It gives me a list of different types of power sources, and it says choose two from the list. Describe one example of an application for each power source. And they've given me an example here. So it says power source, they've picked mechanical. An example, a gearbox is mechanically driven and used to transmit power to the wheels at the correct ratio. Well, for starters, you can't pick that one unless you can think of a different example. Okay, I would steer clear of that to make sure I get my full marks. I think I can think about electrical, and I'm thinking I can think of something for that one. Okay, let's have a look. Okay, so I said electrical, so a power source. Electrical. And then I think back to your lessons, think back to the classroom. What have we talked about? What things in the workshop? Yeah. What have you got as an example of something? Use your knowledge, use your experience in the college to think. So, an electrical power source, the lathe. I've used a lathe, you've used lathes. A lathe is an example. So, and it's not just enough, you can't just put electrical and then lathe, you need to explain. So an electrical motor, I know we can change the speed, so it must be through a gearbox. What does it do? It rotates. To rotate a workpiece. Okay, that's a good example. I've made my point, I've presented an example, and I've explained what it does. Okay, I'm going to leave this one. Have a think for yourself. Okay, see if you can come up with something. Okay, now I'm going to pick pneumatic, and that's to do with air. Okay, and an example of pneumatics that I might be familiar with, for example, the doors on a bus or train. I've heard those. You can hear the air hissing when they move. Okay, so now I know that they're called cylinders. A better word, cylinders or actuators. Fill with air, which pushes a lever to open the doors. Okay, power source done, example done. Yeah, good, solid answer, possibly going to be worth my 2 marks. I quite like this next one. So it asks us to, using the given example of a gearbox from C. Okay, so I'm going to go back through the paper. That's this example here. A gearbox is mechanically driven and used to transmit power to the wheels at the correct ratio. Okay, using the given example of a gearbox, describe, look, it's worth a couple of marks here, how the output is produced. The output, so there's going to be think input to output. How's that going to happen? Well, what do I know about gears? And this is the next bit of advice, if you will. Think like an engineer. Okay, think about your engineering lessons. Driven gears, driver gears. You're trying to show off your knowledge here. Okay, so think about it. Think about it like an engineer. So I know that there's simple gear trains, and you know, these little sketches, they won't hurt your question if you want to use a little bit of space. And we have compound ones, you know, where the gears overlap. So we'd have drivers and driven. So given these, given, describe how the output is produced. So there's rotary. Think about your motions. The 4 types of motions. Okay, we'll do those down here in a second. Do a little bit of a revision session. So rotary motion drives a gear. Drives a gear which transfers power through the gearbox. A large gear would drive a smaller gear faster. So I'm sort of describing, when it's talked about the ratio, I'm trying to describe the rotary motion transfers through the gearbox. A large gear would drive a smaller gear faster. So I'm sort of showing that you get an increase in speed. Okay. Now we've talked about those types of motions, so let's just slide down here for a second. We've got rotary and we've got linear. And then sort of associated with these, we've got oscillating, which is a sort of rotary motion that moves backwards and forwards like a swing. And then we have reciprocating, which is linear but backwards and forwards. So again, useful to know these. Good vocabulary to be used in your questions to demonstrate knowledge, so that you can show that you're thinking like an engineer. Right. A roller coaster takes 2.5 seconds. So this is a question 2. So let's just establish a point there. So we're into a whole new section now. So this isn't levers and gears and pulleys anymore. It's something else. Again. So RTQ. Read the question. Roller coaster takes 2.5 seconds. 70 meters of track. Constant speed. Calculate the speed of the roller coaster. Use the formula velocity distance over time. Well, they give me a distance and they give me a time, and it says, this is really important, state the units in your answer. Well, I'll tell you, it's very good to always put your units into everything. So the velocity v is equal to distance 70 meters over time 2.5 seconds. So that's going to give me 28 meters per second. Okay, you can also write it like this if you want to be, again, think more like an engineer. -1, like that. So we're on to a theme, and this theme of this question too is the roller coaster. So let's have a look at what they're asking. So we've got a diagram here. It shows a pneumatic braking system for the roller coaster. Pressure is applied by component A. Okay, here we go. So these are sort of the brakes, if you will, to a friction plate to slow the roller coaster using friction. This plate attached to the bottom of the roller coaster car and passes between the friction plates. Okay, so here's a good point to stop. Use your imagination. Visualize. Okay, take a minute to think about how that's going to work. Look at the diagram, think about real life experience, try and get you sort of in the right space. Okay, so roller coaster's coming up, this is on the bottom, these sort of be at a fixed point in the track, and we grab hold of the bottom of the roller coaster, and the roller coaster stops. State 2 forms of energy that will be produced during the braking process. I had to really think about this, and what I do remember is when things are stopping, they screech. And actually, sound is a form of energy. And the other thing I can think of is friction. Wherever I know about friction, yeah, you want to just check, rub your hands together, what happens with the friction? You get heat. And a better word for heat? Thermal. Thermal energy. So sound energy, thermal energy. And this is a point where I would suggest that we go and revise energy. Go and look at BBC Bite Size. BBC Bite Size, great for sort of physics and chemistry and science and engineering and design, and go and look up types of energy and how energy works for that one. Name component A. Okay, now I used question earlier, pneumatics, because I know what that is. It's a cylinder or actuator, that's the proper term. And I noticed something else, it's labelled the air ports. So you can put air in and it moves out, and you can put air in this side and pull it back in again. So it's a dual or two action cylinder actuator. Now, this is going to be a little bit of new knowledge. We're coming into pneumatics, and I'm going to actually be doing a separate video that deals with pneumatics and hydraulics and components. But I'll just give you the answers to this, just so that you sort of get you started, and then we can continue with the paper. So this basically, this symbol is air going in. So it's an air input. This is a solenoid, so it's some sort of electrical switch, and this one's a lever. You can imagine someone's hand pulling on that and pulling it backwards and forwards, so it's a lever. So for manually, it's D, and for automatic, it definitely B. You'd have some sort of air circuit feeding air in automatically, or possibly you might get a mark for the solenoid because it is electrical. but I would definitely go for B because we're talking about pneumatics. So a pneumatic system is going to be air controlled, so that's the better answer for the automatic. And the questions continue on the next page. Describe a system that could be used to apply the brakes to the roller coaster automatically. Again, we're back to imagine and visualize. Okay, you've seen the piston. If you look at the diagram, the air's got to go in. Yeah. Now we know that that's a lever, and we could use possibly some electrical or some sort of valve and air input. I'm thinking about this and thinking, well, it's sort of systems and control, if you will. You know, we need some sort of input signal, process, and output. So perhaps some sort of sensor on the track, maybe a laser, and then when the beam's cut, look, I'm looking for 3 marks. The sensor on the track, when the beam is cut, a signal goes to a solenoid, which input process, signal goes to the solenoid, output, which allows air to the brake cylinder. Excuse my rough writing. There we go. I think that would be how I would visualise that. And then notice again, we're on to question 3. Okay, so enter a new question, new diagram, shows a mechanism used on a bicycle. Something I'm sure you're probably familiar with. State the name of the rotational force when the pedals are operated. So the force that's being applied here is a rotational force. Now you might be tempted to think, well, we've got a force times a distance, it's a moment of force. But it's really important that you learn special terminology for rotational force. It's torque. Okay, so when we're talking about a force that's being applied, it's torque. You hear about this when we talk about cars, how much torque a car's got. It's the rotational power that the wheels put down onto the road, and how much torque that they've got. So state the name, it's torque. You need to learn that one. So, yeah, learn it. Calculate the velocity ratio for the mechanism. So velocity is a speed thing. That's going to turn, it's got 48 teeth, and that's going to turn, and it's got 28 teeth. Now, you should know the formula for this. And again, if you don't, it's time to go away and learn these things or practice them. So, I mean, the formula is, velocity ratio is driven, which is this one, over driver. And 28 divided by 48, which is 1 to 1.7. So 1 turn on the big wheel is going to give you 1 and then 0.7 of a turn on the little wheel. So there's your velocity ratio. Now describe the effect of increasing the number of teeth on the driven gear. So you've got 28 here, and again, a little bit like the lever question, why don't you just check it? Why not put a few teeth extra? So go 28, let's go 30. I'll just do a little experiment to myself. and see what happens to the ratio. So if we look at that, we'd end up with 1 to 1.6. So for one turn on there, you'd get 1.6, so you'd get less turns. So a reduction in the velocity, it would, well, it's reduced. Reduce the velocity. Again, don't be afraid to do a little bit of engineering, just to confirm what you're thinking. It'll help you find the answer. Give 2 other applications that use a geared chain drive. Right, just check. They said bicycle. Those say so. What else would use one? Go-kart, motorbike. Think of any others? Come up with a list. You might have it on a conveyor belt, or something to do with a car engine. You could have cars that have chain drive. They used to have chain drives in sports cars. So there's a number of examples that you can think of there. And then it finished, so there's a question 4 there. Just block that off there. Explain the advantages of using geared chain drive mechanisms compared to other mechanisms. So, what other mechanisms do we know? I want to plan here. So, gears versus, or chain versus gears, pulleys. The advantage of chain is it allows gears to be apart, so sort of less accurate. You think about your bike, it's got a system, so you can have a sort of a gear, another gear, and then you can sort of have a spring or something to sort of keep up the tension, so they don't actually have to be sort of super accurate. Okay, gears be about less accurate. Pulleys, better than pulleys because pulleys have slippage. Now sometimes it's good to have slippage, but sometimes it isn't. They're better than pulleys because they don't slip. Yeah, because the teeth grip into the chain. Yeah, they don't allow it to slip, so no slippage. So what have we got? I've compared, I have. They're better than that. They allow that, so there's at least 2 good points in there, possibly worth 3 marks. Okay, let's have a look. You might not remember these. These are definitely something I remember from riding bikes when I was young, but they might not be so familiar to you now. But this is some form of electrical generator, and it's called a dynamo. Okay, so give the name to device A, generator, and then in brackets dynamo, because that is a more, this again, it's an engineering term. Think like an engineer, it's a generator. Okay, but I'd be tempted, you might know them as a dynamo, but think, what is it actually doing? It's generating. State the energy conversion that takes place to produce light. Well, it's mechanical. No, you don't want to put light because it's mechanical into electrical. It's the electrical energy that produces light, but state the conversion takes place to produce the light, so that's already there. So mechanical to electrical. Okay. And again, this is it's think like an engineer, talk like an engineer. So we've got 3 marks here. So describe how the device in figure 5 is able to produce light, naming key parts. Don't forget to name key parts. So I've got magnet. So let's have a little plan. And a coil. Because I know that if the magnet spins inside the coil, it's going to make electrons or electricity. Or current. That would be a better word to use. So electron current goes through the lamp, so the bulb, or LED. Okay, so that's rotating. So wheel rotates a magnet in a coil. This generates a current which flows through a bulb LED to generate light. Okay, so it's important that you think and plan and then talk like an engineer. And then it's asking us to give an advantage and disadvantage using this type of energy just to power the lamp. So advantages: no batteries, no batteries is no impact on the environment, I suppose. No batteries, it's sustainable, you know, it's there when you pedal. So no waste products, so it's sustainable, it's sort of renewable, no waste. So, you know, environmentally friendly, things like that can be said. Disadvantage. You're only having power when when you're stopped, there's no light. That's a real disadvantage. The final part of this one is a new question there. Device A produces 12 volts to power the 6-watt bicycle lamp. Use Ohm's law to calculate current in the bicycle lamp circuit. V over I equals R. That's Ohm's law. Going to calculate the current. That's that one. So it's V over R. So I equals V divided by R. So I've got 12 divided by, oh, hang on, that's 6 watts. Watts is power. Power is equal to V times I. So, have a think. So, it's not that one. It's power. Power is V times I. And I know what the power is. It's 6 watts is equal to 12 volts times something. Okay. So we need to rearrange that formula. So to get rid of the 12, I can do divide by 12 here, divide by 12 there. So I say 6 divided by 12 is equal to 0.5. Now don't forget your units, amps. So we have 6 watts divided by 12 volts is 0.5 amps. So again, can you see where I started off wrong here? I got the wrong. I jumped to a conclusion, okay, but then I looked very carefully at my units to realise that actually I wasn't talking about this Ohm's law, I was talking about power. Okay, and again, you need to learn these. Yeah, you should know these so that you can spot that sort of problem for yourself to make sure you get your 2 marks, your right answer. And that brings us on to this question, which is a fluid power system. Well, we're talking about pneumatics, and we're talking about hydraulics, and I said there'd be a separate video. So what we're going to be doing is we're going to be looking at that in more detail. So we're going to be looking at this, but I'm going to do that as part of a separate video. Okay, so we'll leave that there, and we'll come back to that in R101 part 2. Thank you for watching.